Okay, in this section of differentiation application, we are dealing with maximization and minimization problem. So what are these kind of problems? So these are the kind of problem that will be translated to real world context. So a very generic one in the real world context will be like canned drinks. So I'm sure you know in the market, sometimes in this kind of canned drink, the shorter one, and there's also a slimmer version of a canned drink. So as a manufacturer of canned drinks, they may be exploring different uh shape. Okay, why do they want to explore different shape? Because the surface area will incur material cost. The surface area will incur material cost. So for example, if they use aluminium to make the can, then if let's say their can has a very large surface area, then they got to spend more money to create the can. So usually the restriction is they would like to minimize the amount of like material used, but they do not want to compromise the volume in the can, because the volume is the amount they sell it to the customer. So in a way, they would like to maximize the volume, because if the volume is maximized, they can sell at a higher cost to the consumer. But while they would like to have as big volume as possible, they also like to have as little surface area as possible, because lesser surface area actually means that they invest lesser in the material cost. So there will be other real world context that sometimes will be incorporated into this category of question. So inevitably, this application will involve all the mensuration formula, and you will need to know the formula at your fingertip. So in the previous one of the application rate of change, you also encounter connected rate of change, related rate of change. You also encounter the various mensuration formula being used in rate of change. So the same set of formulas is also being used in the maximization and minimization problem. Okay, so first of all, this is just an introduction first. Okay, so what kind of question will they be asking you, and what is the approach? The approach is very similar to stationary point. So the stationary point, we set dy dx equal to 0, right? So in this section, you will be asked to find a few types of question, which I will show you in the example. But I'm just showing you a generic idea first. So the question can be asking you to find the maximum surface area, or the minimum surface area, or stationary surface area. So if the question is asking you for this, you got to make sure you got the area with only one variable. That means it must only be x, or it can be in terms of r, doesn't matter. But you cannot have x and r together. You must have a as a formula in terms of one variable. One variable means only x or only r. So you cannot have x and y. Okay, so you must make sure you got such a formula first. And then once you got the formula, you differentiate the expression. So if this is the case, right, I'll be getting a dA dx. If I got it as a r, I will be getting a dA dr. So if you would like to find the maximum, minimum, or stationary area, you set the differentiate equal to 0. So that behaves very much like stationary point. So like stationary point is dy dx equal to 0. So in the finding of maximum, minimum, and stationary R, we differentiate the area equal to 0. So when you do the differentiation, you will actually get a special value of x. So this special values of x is called the stationary value of x. And with the stationary value of x, if you sub the value of x into your formula, you will be able to get the area that is maximum or minimum. So this one can be the maximum area, or it can be the minimum area, or it can be the stationary area. Okay, so they will ask you for maximum area, minimum area, or stationary area. So the procedure is like this. So what happens when they ask you for maximum, minimum, and stationary volume? So if you need the maximum or minimum volume, you make sure you got the formula in one variable. Okay, I'm using X and R as a sample. So you must make sure that you only have one variable. And then same thing happen, you differentiate. Same thing happen, you differentiate. And you differentiate and let it be 0. So once you do that, you get the special X. That special X again is called the stationary value of X. And with the special X, you put it into your volume formula. This will be your minimum volume, or it can be your maximum volume, or it can be your stationary volume. So basically, you keep repeating the idea. The idea is very simple. So you want maximum and minimum of something, make sure you got the formula. Once you got the formula, you execute as if it's a stationary point. You differentiate and let it be 0. So it's very almost the same idea as stationary point. So it's a like a technique. Okay. The most difficult one is actually to find the minimum gradient, maximum gradient, or stationary gradient. Because gradient is not exactly like area and perimeter. It's not area, it's not volume, all that. So in fact, the gradient is represented by dy dx. So the gradient formula is actually represented by dy dx. So in order not to get confused, I'm going to use, usually I will let G be dy dx. Okay, so you get a formula for the gradient. Okay, so it's the same approach. You get a formula for gradient, then you do a dg dx equal to 0. You will get a special X for you to put back to get the minimum gradient or the maximum gradient. Okay, so some of you might be thinking, so if I do a dg dx, wouldn't I get a second derivative? In a way, yes, that's a second derivative. But if you don't want to confuse yourself, you don't see it as a second derivative. You see it as you differentiate gradient equal to 0. Just like in the previous situation, you differentiate volume equal to 0, you differentiate area equal to 0. So it's something that doesn't change. Like dy dx equal to 0 for a stationary point doesn't change. So whatever you want maximum or minimum, you differentiate that item equal to 0. It will help you to achieve the maximum or minimum item that you would like to have. Okay, so after you find the stationary volume or area, sometimes you'll be asked to determine. So the question may ask you, is it a maximum area or is it a minimum area? So we will go back to our first and second derivative test, which is exactly the same as your stationary point. Okay, so we will do exactly very similar to the stationary point where we come to maximization and minimization problem. So that is just a basic introduction first, okay, before I show you the actual example.